Games have existed for multiple millennia, but it wasn't until the mid-20th century that they began to be seen as a serious subject for analysis. One such game is the game of chicken. While it may seem peculiar that this game has any real-world applicability, it can model conflicts such as the Cuban Missile Crisis and commercial disputes such as price wars. What if we could correlate how these situations play out with aspects of the brain's cognition? This is the question that we will attempt to answer. A typical game of chicken has three Nash equilibria. Two are asymmetric pure strategy Nash equilibria, where one player gets more benefit than the other, and the third is a symmetric mixed strategy Nash equilibrium, where both players benefit equally due to probabilistic strategy selection. A Nash equilibrium is an outcome from which neither player individually departs because it would do worse, or at least not better, if it does. Our game is specifically an iterated modified game of chicken. Each game has three distinct rounds. The first is a simple 3-second planning phase, where players can reset from the last game and plan their next move. The next phase is a 5-second decision phase, where the player's cognition is read and aggregated by the brain-computer interface, or BCI, to determine what action the player will take. More on that later. The players have three distinct actions which are left, right, and center. The payoff matrix for this game is displayed on screen, where each outcome changes the player's score by a specified number of points. The final phase of the game is the simulation, where the players can visualize the results of their actions. The symmetric mixed strategy Nash equilibrium has both players playing with a probability of going in the center 34 out of 84 times, and a probability of going right and left 25 out of 84 times. A completely rational player would play according to these probabilities, but we see deviations from this equilibria because people rarely play completely rationally. The player's cognition is measured using an electroencephalogram, or EEG, through the emotive epoch flex. 14 electrodes are used from each device to measure voltages across the surface of the scalp. As mentioned earlier, to convert the player's cognition into actions, we are using a brain-computer interface, or BCI. Our specific BCI works on motor imagery, where the player imagines moving a different body part to signal directions. The game averages the BCI inputs over the duration of the 5-second measurement window. By treating the brain, computer, and game as a closed system, a general function can be derived that takes brain activity and returns brain activity at the next point in time. One particularly novel method of creating this function is dynamic mode decomposition, or DMD. We apply DMD directly to the EEG signals from both players. Traditionally, DMD is constructed from creating two matrices, X and X prime, from M snapshots of data. We can then create matrix A that contains a high-dimensional linear regression such that X prime equals A times X. Dynamic mode decomposition is the eigendecomposition of matrix A. While it is possible to obtain an approximation of matrix A using its pseudo-inverse, we follow the more scalable approach displayed here. We make some alterations to DMD to make it more suitable for EEG signals, such as augmenting the matrices X and X prime and scaling the modes by energy during the decomposition process. Dynamic mode decomposition associates spatial modes with their dynamical oscillation, which is why each mode or column of matrix phi corresponds to exactly one oscillation or point on the diagonal of matrix lambda. In our case, it makes the most sense to convert these dynamics to cycles per second or hertz. Furthermore, because we scaled the modes by energy, the power of each mode can be found by taking the square of its vector magnitude. Now we can visualize important results, such as the qualitative resemblance between the dynamic decomposition mode power and the power spectrum computed by the fast Fourier transform. Previous studies have attributed certain actions with specific frequency bands, such as the correlation between beta band connectivity and defecting. These findings indicate that DMD modes with dynamic frequencies in the beta range should show a statistical difference between brain connectivity during the swerve and don't swerve actions. Furthermore, because of the closed system interaction of players, the equilibrium reached in their game should correspond with their beta band modes. Specifically, players who tend to play cautiously and swerve more often should have statistically different beta modes than those who play more aggressively and avoid swerving. We can extract modes that correspond to beta band oscillations and some corresponding modal components across each of these modes during different phases of the game to confirm these results. Though we do not yet have trial data, preliminary data collected while testing the game shows very specific modal patterns in the beta band while playing center and different modal patterns while playing other actions, indicating there could be a statistically significant difference in calculated modes. Once trial data is collected, we will be able to make a more confident statement on the modal decomposition of brain cognition. If you have any questions or want updates on future results, please contact myself or Dr. Zhu. Thank you.